Hello, everyone. It's my pleasure to greet all of you, as well as Brian, who will be giving a talk in a moment. Before we get to the talk, I actually wanted to talk about the QRE challenge that we are organizing together with a couple of other people. And basically, it would be nice to, so we thought we're talking with Brian, and Brian gave this talk at the Unitary Fund some time ago, and we discussed that it would be nice if actually it was recorded and published, as this would be a good intro to some of the resource estimation tools, and could be good for people who want to take a part in the challenge. So what is the challenge? Together with some folks, we are organizing workshops on resource estimation at IEEE Quantum Week in Montreal in September. So if anyone plans to go to that conference, please come to see our workshops and participate in them. If you are not planning yet, I highly recommend it. It's a great conference. Been there twice, and it always have been a great experience. We don't have all the speakers confirmed yet, so I'm not even showing the program. But one of the, we discussed with the other organizers, who are listed here, especially Maria, proposed that it would be nice to maybe prepare, throw a QRE challenge. So basically give some task to community, so that people can try out different tools, get some experience in order to popularize those tools, as well as educate people a bit more about the topic. So we decided to do that, and it's ongoing. The challenge is ongoing. So what the challenge is about? Basically, it's go and do a project using available QRE tools, and these are all the tools that Brian will be talking about. It's pretty open-ended. The basic idea is select a use case, select an algorithm, go and try different tools and see what you get. But because the topic of QRE is pretty wide, you can focus on many different things. Depending on what your interests are, you can focus more on the application or algorithm side, or compilation, or error correction, or even hardware modeling. There is plenty of opportunities. So the deadline for submitting is end of July, and then in August we'll be reviewing all the applications, and we will be we'll have presentations, and then we'll select the winner, and the winner will be invited to present at the conference. Unfortunately, we cannot cover the costs, but there is a slot in our workshops where you will be able to present your work if you win. More details about it on the website. I don't want to spend too much time on this. This is just like a short advertisement. Speaking of advertisements, there is also another resource estimation workshop organized by Alexandru Paler, Simon David, and Daniel Herr, which is happening also in September in Helsinki. Please come check it out. It's a great, I've been there before, and it was a great event. So also for QRE enthusiasts, and it actually might have a reasonable remote access. So but I don't know. It depends how the rest of the conference is organized. So check out their websites, and that's basically it. And with that, I will pass it to Brian. If there are any questions, please ask them in the chat. I don't want to take too much of his time. Or you can always ping me or Maria or any other organizers really separately. We are easy to find in the internet. I'll be posting the links in the chat in a moment. So Brian, the floor is yours.
Okay, let me go ahead and share. So this is coming out of work that was done as part of the Quantum Open Source Foundation's mentorship program where Maria was actually our mentor, and I did the work with Arnav Sharma, who now works at MIT Lincoln Lab under Kevin. And the outline, we're going to just go over general quantum resource estimation, what it is, why it's important, and then we're going to jump into the 4 tools. So first of all, for quantum resource estimation, kind of what it is, it's going to be gathering the estimates to accurately run the algorithm. So that's going to require large-scale, error-corrected quantum computing with reliable logical qubits and fault-tolerant operations. And in regards to what are the resources, it can vary between the tools, but it's everything from the number of T gates or rotation gates or like you can see there, the logical qubits, physical qubits, time. And again, depending on the tool, you can even get stuff like the power, which is really kind of interesting to be able to gather that, which is pretty cool. So for why it's important, first of all, it's helpful to understand if an algorithm can be run on today's hardware, or if not, how far away is today's hardware from what would be needed to run it. And while it's less important today because of where hardware is at, it's going to be increasingly more important as that gap between the requirements and the hardware capabilities narrow. Also, the estimations are really helpful for showing the trade-offs between the time it takes to run an algorithm and the number of qubits needed. So if a particular algorithm requires a minimum of, let's say, 1,000 logical qubits, but the runtime is super long, you could see, okay, well, if we adjust that and let's say give it 3,000 logical qubits, you can see how the runtime is going to shrink because of that. And so that's really helpful as well. And then certainly not last, but it's really important to show a comparison. And the comparisons kind of can refer to a few different things. You can compare quantum resources versus classical resources to verify the quantum advantage. But you can also compare different different implementations of the same quantum algorithm to see, okay, is this new version better? Or even it could just be a component of the algorithm that could be updated. And you can see, oh, if we adjust it, is this going to require less qubits or less time to run? And so it's getting the resource estimates is very useful. And the tools we're going to talk about are, again, the 4 that are part of the challenge: pyLIQTR, Qualtran, BenchQ, and Azure Quantum Resource Estimator. These aren't the final list of tools that are out there. These are 4 of the big ones, and they are also all open source, which is pretty cool because you can go and look at the code, you can submit issues, you can work on issues. And it's pretty amazing that so many of these and so many of the big ones are open source. It speaks to the community that Michal and others are kind of leading the charge on this and making sure that things are open source, which is pretty awesome. So starting with pyLIQTR. pyLIQTR is out of MIT's Lincoln Lab. It's a Python library, and it lets you build quantum circuits for certain algorithms, as well as generating Clifford plus T estimates. So it's built on Cirq, so it takes Cirq circuits, and it uses things from Cirq-FT. So like the decompositions are ported over from Cirq-FT. And Cirq-FT at this point has actually been deprecated, and that functionality has been rolled into Qualtran. But like it says, pyLIQTR has actually been used that already. So, and one of the cool things are the problem instances. So pyLIQTR has the ability to create these problem instances. So you're able to encode different Hamiltonians. And so it has all these different implementations of specific types of Hamiltonians that the tools are kind of built in there to easily generate those, like in XXZ Heisenberg, for example. The tool also has block encoding for those Hamiltonians, which is also super useful. And another very, very helpful thing is the quantum signal processing and quantum singular value transforms. And the pyLIQTR has the tools to generate those and generate the operating sequences for those. And those are, and if you didn't know, they're protocols for helping you calculate arbitrary functions for Hamiltonians and other operators. And they're common in as subroutines of algorithms. And pyLIQTRs can generate those operating sequences for you, which is very helpful. And as mentioned before, pyLIQTR decomposes things down into Clifford plus T for resource analysis. So it is staying at that logical level, and it's not going beyond that. So if you look, for example, at the circuits there where it is mentioning the QSVT, that quantum singular value transform, you can see the circuit on the left has it at kind of that higher abstracted way. And then if you run a decomposition on that, you can see the circuit on the right where it's actually breaking it down into kind of the lower level gates, like you can see the controlled X gates and the rotations and things like that. And you can continue breaking things down until it gets to just that Clifford plus T level, which is very helpful. And you can see an example of kind of the output where it's showing the logical qubits there, and then the number of T gates and the number of Clifford gates. But again, it is staying at that logical level. Mikhail, yes.
Yeah, so we have a question in the chat, like what does the problem instance actually means?
So what that's referring to is kind of the different Hamiltonians. So pyLIQTR has the tools for generating those problem instances and those different Hamiltonians. So you're able to provide just kind of minimal information, and it's able to generate those problem instances for you. And just as it's able to kind of generate and build those up, obviously it can break them down and decompose them as well. And there's a bunch of them. If you check the pyLIQTR documentation, you can see all the different ones that they have. And you'll also see this kind of come into play later in BenchQ as well, as a little spoiler alert for what's coming up.
And also a question from Sean, how are repetitions handled in pyLIQTR? Because like QSVT is not just one repetition. It's, many repetitions of the same kind of block encoding. In the picture, we only see one, right? So
yes, I'm not exactly certain on how that is handled. Yeah, I'd recommend checking the documentation on that as well.
yeah, Athena is saying that last time she checked, it gives like the whole circuit and doesn't handle repetitions in any kind of it's like automated way. And that's also what I remember from the past.
But I will say that, like, since I've dug into it, they have done a 1.0 release, so it's very possible they've added these nice features like this. So I would check, but last time I checked, the answer was write out the whole damn thing.
Yeah, and that is something to note, which is all of 4 of these tools have seen significant updates, like since the beginning of the year, there have been changes throughout. So it is something that you would, if you're really interested in the details, check what the latest version has, because I mean, even just a week and a half, 2 weeks ago, BenchQ released new things. And so it is helpful to go and check and see what is the very latest. So next, we're going to talk about Qualtran. Qualtran is from the kind of Google ecosystem, and it has its own paradigm for constructing circuits called blocks. And blocks can be then combined and come up with composite blocks. So a small example there you can see is a CNOT block, where there's two registers on the left with the control and the target, and then you can see the two registers on the right. And then you can get the estimations out of that. And this is a way of keeping track of the operations you're using and how many qubits are coming in and coming out. And again, as a CNOT, that's kind of like an elemental operation, and it's one of the pre-built blocks. But you can, as mentioned, stitch them together to have composite blocks, but you can also create your own. And that way you do kind of have that control over it as well. So an example of kind of the composite blocks is over there on the right with the multi-and composite block. And you can see how you can then decompose it. So there's the multiple and you can decompose it into 5 and blocks. And then you can continue decomposing that. And you can see, okay, well, that's going to be 9 arbitrary Cliffords and 4 T-gates. And so it's pretty helpful for that to kind of organize and see that. And again, there are the pre-built blocks, like you can see the CNOT, or and rotational gates are also kind of considered one of those pre-built elementary blocks. And then there's also Toffolies are also considered elemental as well. And so the decompositions, again, as I mentioned earlier, circ-FT has been deprecated and that functionality has been rolled into Qualtran. And so it's obviously going to use those decompositions as well. Again, it makes sense as it's all part of the Google ecosystem. So you can build your own composite blocks and define them how you would like. You can also take a circuit and translate that into blocks. And so it's especially the ability to build your own is kind of helpful, because that way, if you wanted to build a certain circuit or operator in a specific way, you could. If you wanted to just use high-level operators, you can just build the blocks for that. And so then you wouldn't have to go as low. But also you could limit yourself to a specific hardware gate set as well by doing that. And again, speaking of updates, a couple months ago at this point, Qualtran introduced an Azure cost model as well as a CCZ model in order to go from those logical estimates down further down the stack in order to get physical estimates. And so by doing that, Qualtran actually ends up integrating and working with Azure Quantum Resource Estimator by providing those logical counts and that logical information. And then the Azure Quantum Resource Estimator is able to go further down, like I said, and provide physical estimates. And then another, I think, useful thing to point out is that Qualtran gives you a lot of very useful pictures. So the block structures that you're seeing there, those can be printed out of Qualtran. And it's very helpful, again, for just organizing it and being able to get a picture of how the circuits are kind of decomposed as well as built. So that's also very helpful. Next, we'll be talking about BenchQ. BenchQ is developed by Zapata, and it came as part of the DARPA quantum benchmarking program. And kind of the unique thing is the implementation of the graph estimator that uses graph states or cluster states. And so BenchQ takes in a quantum program, which can be an existing Qiskit circuit or a circuit or an orchestra circuit, which is Zapata's kind of ecosystem. They use orchestra circuits. And another way to get the quantum programs, though, is through what they call problem ingestion and problem embedding. And that's where, as mentioned earlier, BenchQ actually uses pyLIQTR and Open Fermion to easily create Hamiltonians. So like molecular Hamiltonians or plasma Hamiltonians, all these different ones, you can easily generate those with like a line or two of code. And then you can take those and use the problem embedding, which uses pyLIQTR's like quantum signal processing, Open Fermion's quantum phase estimation. And then they also have their own algorithm implementations like QAOA or trotterization. So you can easily use those to generate your quantum circuits. So if you didn't already have a Qiskit circuit or orchestra circuit, you could easily generate those and just a few lines of code with their problem ingestion and problem embedding. And once you have that circuit, that is going to be compiled down into a graph state. I'm not going to get into too much of the details of that because it would take a lot of time. But the important thing with that is that it can be mapped onto the surface code, which is going to go lower down in the stack. So rather than just stopping at that circuit level, it's going to where it's going to try and map it onto the surface code. And that's going to get you estimates that are more accurate. And it's then going to obviously bring in the hardware and all of that once it's been mapped onto the surface code. But yeah, so that's incredibly helpful. And as you would imagine, though, compiling it down to the graph state and as well as mapping it onto the surface code and optimizing it, it can take a lot of resources. And so they have kind of different versions of their graph estimator to handle that. And they also have, to help you out, they have an automatic resource estimator where you can pass in the information that you, like the algorithm and the hardware model and all of these things, and it will say, okay, this is the one that you should use because of the size and depth of the circuit and different things. So that will tell you which one to use, which is very helpful. And also, BenchQ does integrate with Azure Quantum Resource Estimator as well. So if you just were looking to easily compare, which again, for this challenge, that seems like it'd be really useful and give you useful information, you could easily take something and use BenchQ's graph estimator and then write in that same code, connect to the Azure Quantum Resource Estimator, and then get two different results and be able to compare it, which is pretty useful. And like I said, for this challenge where something like that is going to hopefully provide interesting results, that's something you would probably want to do. An example of the output from BenchQ is given here. This particular one is using the detailed ion trap architecture model, which is using actual information from IonQ for the ion trap stuff. And it's really interesting because you can see the level of detail that they're able to give, and you can see that it's not only giving you the number of physical qubits and logical qubits, but with the detailed hardware information, it's able to tell you power. And it's pretty amazing that you're able to get all of that data from it. Again, this is using the detailed ion trap architecture. There's a basic superconducting one as well as a basic ion trap one that doesn't have all of that data, like I mentioned. This one has from IonQ, but you're still going to get a lot of information from this. And next, we're going to talk about Microsoft's Azure Quantum Resource Estimator. As we've already mentioned it a couple of times because of the other tools integrating with it. And this graphic, I think, is pretty helpful just in general of understanding the stack and seeing kind of how resource estimators are going both from the top down as well as bottom up in terms of going from kind of that high level algorithm or circuit and then getting down to those logical estimates, and then using the hardware information and working backwards to then say, okay, well, now that we have all the hardware and error correction information, we can then use those logical estimates to generate physical estimates as well. And obviously Azure Quantum Resource Estimator is doing things well if a number of other tools are integrating with it. And the Azure Quantum Resource Estimator takes by default Q# or Qiskit code. If it is Q# and you're most likely using VS Code. If you use the Azure Quantum Development Kit extension, you can pop up a new tab super easily without having to change or tell your code to do anything to generate the resource estimators. You just go to the command panel thing, and I just know the shortcut keys, but the palette, there you go. And it will open up a new tab with the estimates, which is, again, just an easy way to do it. The only problem with that is that the estimates are not programmatically accessible. So you can look at them, but you can't then make your code do something with those estimates. But there are other ways to do that, whether you're using the Python, the Q# Python package, you can do that, where you can it can read the Q# code. For Qiskit, there's actually a Qiskit backend that for the estimator that does require an Azure Active Portal account, because it will go out and use kind of the Azure servers to generate that. So also what is nice is that you can use other inputs as well. So what will happen automatically with Azure QRE is that it'll take your circuits and translate it down into quantum intermediate representation, QIR. If you already have that, you can just use that directly. That will require you to use the Qiskit backend, but again, if you have those, you don't have to worry about kind of the algorithm at that higher level. Also, once you're at that QIR level, it breaks it down into logical estimates. And similarly, if you already have those logical estimates, you can just use those directly. That's actually what Qualtran is doing. It uses the Q# Python package and uses those logical estimates and just takes those and kind of jumps ahead and skips to that level, which is nice because then you can use the stuff lower down the stack like we mentioned, where you're going to specify like the physical qubit model and the error corrections and all of that to get that info. And one of the things that's really helpful and useful is the flexibility of Azure QRE for all of the different things like the physical qubit models and the error correction schemes. All of those, there are some pre-built ones in there, and you can customize an individual parameter or multiple parameters, or you can even just go ahead and build your own. So if a new paper comes out and it's using, it just comes up with some other kind of claim, or it has a different, it could be anything from like the qubit measurement times, or the T-gate times, all of those things. You can customize that for all of them, which is very helpful. And it really allows you to play around with it. And as kind of the point of the challenge is to play around and test things out and try and get useful information, this is another way of being able to do that. And again, the tools that tie into Azure QRE, you can still use all of these customizations here at the lower level of the stack, which is pretty helpful. So if you're using Qualtran and you're planning on using the logical estimates from that, you can still use the flexibility of the distillation units or error correction scheme here. The constraints are also interesting in that lets you play with the trade-off between the number of physical qubits and runtime. Like the other tools, there's an emphasis on speed over the number of physical qubits. But if you did want to adjust and play with that, you can do it in different ways with those constraints, as opposed to just saying, I want to emphasize the number of qubits. So you can get in and play with that, which is pretty cool. And then the results that you get from Azure QRE, especially if you're someone new to quantum resource estimation, I think these are very helpful because they explain a lot of the results that you're seeing there. So first of all, if we look over on the left, that is if you're using the VS Code extension, this will happen by default. It's called the Pareto Frontier kind of functionality that they have in there. And if you were doing these manually, like I said, either through the Qiskit backend, or if you were doing in Python, you can also tell it to do this. But it's really cool to show the trade-off. It's automatically showing you the trade-off between the number of physical qubits and the runtime. So you can see there, okay, well, if I increase the number of physical qubits, my runtime goes down, and you can click on each one of those points to get the specific details about that. This also shows you how you can do batch estimations. So this is actually using different physical qubit models here, and showing you how for this one algorithm, you can choose different physical qubit models, and you can set up your error budget, and you can see how they would perform differently. And over on the right, that's showing the kind of the data. It's showing as well as how they're getting the data, which again, if you're new to resource estimation, it's helpful to see, okay, well, you're telling me that there's this number of logical qubits. How did you get that? Well, you can actually see they'll detail that information. And I think it's very helpful to see that. And again, the batch estimation, again, as we're talking about the challenge and trying to test things out and find interesting things, that's going to be a very useful way to do that. And as mentioned, the tools that integrate with this, the Azure QRE, you get back this information as well. So yeah, so it's very useful and helpful. This slide is just kind of a useful overview of the things that are discussed. So for what the inputs are, you can see it right there. So if you already have your algorithm written in Qiskit, you can be like, okay, well, if I don't want to have to worry about writing it in in Circ or something else, you can see here, oh, okay, I can use BenchQ or Azure QRE off the bat. And then pyLIQTR is, again, just stopping at that logical level. And the other tools are going down to the physical estimates as well. And then you can see the highlighted features there, the things that really gives, that makes the tool stand out and what's unique about them. And yeah. Again, I'd like to thank Quantum Open Source Foundation for setting up having the mentorship program. It's absolutely fantastic. Maria, who was our mentor, Arnav, obviously, for working with me on this is great. And Athena and Peter, we had conversations with them, they're very patient. And that's the other thing. Again, if anyone is new in resource estimation and finds it intimidating, everyone we've interacted with has been just so patient and welcoming and encouraging. So whether you're joining the QRE Discord server or whatnot, feel free to reach out to people, and they've all been very, very helpful. And were there any more questions or anything else in the chat?
Awesome. No more questions in the chat, I think, right now. So do we have any questions from the audience? We have quite a bit of time for discussion. So I have some questions for Brian, but want to first give other actually opportunity to ask there. So if so, just like please raise your hand, unmute, and ask the question. Before I see Jackie has a question in chat. Has there been any work on Qtreat QRE? I think the answer is no. At least I haven't heard about anything, and it doesn't seem to me. It's like it's complicated enough as it is. So I don't think a lot of people are actually investigating Qtreats in this context.
Yeah.
Okay, so I have a question. Since there's no one else yet. My question is, if someone is new to the topic and would like to, just like they have no preferences, over picking one library to the other, which one do you think is the easiest one to start with, and why?
So if you haven't implemented your algorithm in anything yet, because again, if you already have it implemented in something, then that's going to help you choose which one to use. I would say to start, I tend to say if you're not familiar with them, to look at the Azure QRE one, because especially with the descriptions that they give for the estimates, it really helps you to understand where they're coming from. And I think that's a good place to start. And hopefully once you get familiar with that, then you could look at, I would say, using one of the ones that tie into that. Like with BenchQ, we talked about how pyLIQTR, one of their main things is breaking things down into Clifford plus T. Well, BenchQ can use that. So you can use pyLIQTR's decomposition to Clifford plus T, and you can use the graph estimator in BenchQ. And then you can also use the Azure QRE integration in BenchQ. So then if you kind of get that foothold in with Azure QRE, I think then you can bounce to the Qualtran or the BenchQ, and you're like, okay, I already understand that part at least.
Thank you. Athena, you got the question?
I did, but you asked it, so I'm going to ask a different one. So I guess a lot of this is about QRE tools, but at least for me, at least like for a lot of people here, one of the most valuable bits of information that they have is like, that everyone have is like, you know, how do you learn more about QRE, right? Like, can you explain a little bit more about your journey and like, you know, who were the key players in explaining this stuff to you, and like, and how much do you feel you understand now after going at this for at least a couple months?
So when I started, I didn't know anything about it. And I mean, to the point where I knew roughly about T gates, but I didn't know why they were important, why they're considered more important than the Clifford gates. So I mean, I started at a very, very, very low level. And a lot of it has been reaching out to people on the QRE server and even just saying, hey, I'm interested in this. Can you point me to something? And then like when I reached out to you and Peter and Mikhail, and they said, oh, if you're looking at I mean, for the graph estimator, that was kind of a beast in itself. And because there's the measurement-based quantum computing, I hadn't looked at that at all. And I mean, if you're going to go down that route, they're actually, Athena, you had a good post, and other people did on the Discord server as well, talking about, okay, we'll start with the game of surface codes paper. Well, even really start with the video, because that reading the papers are not necessarily very easy. If you're not coming from a PhD background, because I did undergrad in computer science, and after working in the software industry for 14 plus years, I went back and got my master's in computer science. And this whole world is so heavy in the physics still, which makes sense. I mean, if you were going back to classical computers in the late 50s and 60s, you're going to need to know the electrical engineering side of it. We haven't abstracted that away yet. So Microsoft actually has a really good kind of higher level paper as well. And actually one of the graphics that I took from it. So if you're coming from a computer science background, that does help, because it does compare the classical and quantum kind of stacks and how that works. But reaching out to people has been super helpful, because especially if you're coming into this field and you're not coming from a PhD program or something like that, it's very intimidating and scary and lonely. And so the open source communities, whether it is the QRE server Discord, the Unitary Fund, reaching out to people and saying, hey, can you help me out? Or do you have suggestions? Like I said, everyone has been very welcoming and very patient, and I think that's really a good way to go.
I also wanted to reiterate on this point that there is, you know, this kind of tension here between all of this being really cutting edge research, and you know, a lot of the ideas when we were working with Athena on BenchQ, a lot of the things that we implemented were not even, you know, written down in any paper. We're just taking notes from Simon David directly and just like implementing that in code. So this knowledge is like very, very scarce and scattered. But at the same time, because it's so early, because you know we're trying to kind of collectively build this community, if someone actually starts using these tools and is interested, people are, as Brian said, very welcoming and very open to conversation. So if, for example, you know, open one of those repositories, start playing with that, and you see that, well, the documentation is scarce at best, and you don't know exactly what's going on, well, then just like write an email to the authors, and or find them, you know, on the Discord or like elsewhere, and try to connect with them, because for them, like for us, I'm also kind of working on this kind of software. User feedback is just like extremely useful, and we want to make those tools actually useful for people. We want to, you know, push the kind of boundaries of like current research, and if we don't get feedback from people, then well, we won't be able to do that effectively. So I think it's like really important not to get discouraged, and as Brian said, just try, just like reach out to people, ask questions, and you know, both sides will be happy. One that, you know, there is interest and they get feedback, and the other they get all the answers they want. So yeah.
And as you mentioned, there's quantum computing in general has so many different little kind of niche areas, and I wouldn't have guessed back in November when the whole cohort started that I'd be presenting and talking about this. And weirdly, just by spending that time and effort in here, I have knowledge that's useful to experts, but they're not experts in this particular niche area. And so it's, if you're willing to put in that time and effort and really dig into stuff, you can find kind of your own place, and you'll find that there's a small community, and then it slowly grows bigger and bigger as you learn more and more, you meet more and more people, and it's a fun adventure. It's hard, but it's fun.
Yeah. Do we have any other questions? Please don't be shy. Okay, I have one more. So I would, I'm wondering, and you know, don't want to. Okay, so I'm wondering what was the biggest challenge when, you know, working with all this software? Was it actually, you know, the fact that it's not like the knowledge is scarce and it's like hard to actually, you know, learn what it is, or was there something else?
I think it's that at this point you still have to understand a lot of, or at least some of the lower level stuff. I mean, my early conversations and emails with Athena, some of them I look back on and I'm just embarrassed at how how I wasn't making connections and stuff, because you do need to, even though you're not obviously working on any of the physical hardware or any of that stuff, you need to have a general understanding of a lot of very technical things. And like we're talking about the Hamiltonians and the different kinds of, there's some of those I'm just saying the words and I don't completely understand a lot of that information. And I think that's kind of the part where it's try not to get discouraged, because there's so much that you don't know, and you just kind of have to keep going and keep asking questions, and it leads to those connections. I remember when I finally got what they meant when they said that BenchQ goes lower down the stack, and why that gives you a closer to hardware and gives you a more accurate estimate. I remember when that finally clicked and I was like, oh, that I get why that matters now. So it's a lot of reading, going through the documentation, going through the code, and asking questions. And like I said, I know it's scary to ask questions. I mean, it's weird. The people that I've now interacted with quite a bit, I remember when first thinking of talking to them and being so nervous. And it's funny because it's you guys and Maria. And I remember I went to the IEEE Quantum Week last September, and I had talked to a couple of Unitary Fund people on their Discord server. Other than that, I did not know a single person. And having to go up and talk to people and thinking you're these experts and yeah, and being just crazy nervous. And then I'm sure, like I said, I see why you're laughing and I get it, but it's, you just kind of have to push through and like I said, everyone's been so patient and welcoming and no one's been like, oh, look at this dummy, he doesn't know it. So yeah, it's really, the community is a big part of all of this. And yeah.
Awesome. Thank you very much. I think it's pretty like encouraging, hopefully to people. And yes, as Athena said, we spent most of our time as that dummy ourselves, and we only sometimes are kind of don't feel like dummies. So this is kind of the big secret. Anyway, if there are no other questions, I think we can finish here. So thanks a lot, Brian, for this presentation. I think, is really, really useful. We'll definitely be, sending that, link to the recording to a lot of people. If just a reminder, if you haven't checked it out yet, please check out the, the QRE challenge website. If you cannot find the link, let me know and I will send you a link. And yeah, that was, really, really nice overview. Thank you very much. And I wish everyone here a great day.
Thank you.